Most of us will talk calculus as a list of rules, differentiate this, integrate that, don't forget the constant. At some point, we just accepted it, memorized the formulas, and hoped that exam questions looked familiar. But that's not calculus, that's just symbol pushing. Calculus is one idea with two versions, and once you see it, the formulas stop being mysterious. So, what is calculus actually doing? Not the mechanics, not what the textbook says, the idea underneath all of it. Newton worked this out in about 18 months while sheltering from the plague, and he wasn't memorizing rules. He was thinking about curves, motion, and what happens when you zoom in very, very close. Most people, when they hear calculus, think of formulas. The derivative of x to the n is n times x to the n minus 1. The integral of x to the n is x to the n plus 1 over n plus 1 plus c. You probably drilled these until they felt automatic. Knowing them is fine, but there's a gap between knowing the tool and understanding why it works. If all you have is the rule, you're stuck at the moment the problem changes shape. If you understand where the rule came from, you can handle things you've never seen before. Calculus has two ideas. The first, zoom in on a curve until it looks straight. That straight line has a slope, and that slope tells you something real about how fast something is changing at that exact moment. The second, fill an area with thin strips, add them up, then make the strips thinner until the error vanishes. Everything else, every rule, every technique, is one of these two ideas applied to a specific curve. Take any curve, pick a point on it, now zoom in. Not a little, really zoom in. Keep going. The curve starts to flatten, the bend disappears, and at a small enough scale, every smooth curve looks like a straight line. This isn't an approximation, it's actually what smooth means. And that straight line has a slope, and that slope is the derivative. To calculate it, pick 2 points on the curve and draw a line through them. The slope of that line is rise over run, how much the curve went up divided by how far across you moved. Now slide the second point towards the first. The line rotates, and as you keep sliding, the gap h gets smaller and smaller. And at the limit, when h has shrunk as close to zero as you can get, the line stops rotating. It's just touching the curve at your point. That's the tangent line. That slope is the derivative, not approximately, exactly the derivative. Written out formally, it looks something like this. F dash x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h, which is rise over run with the run shrinking towards 0. The top is the change in f, the bottom is how far you moved. The limit is just keep shrinking the bottom until the answer settles. One fraction, one limit, and that's the whole thing. The second idea is about area. Now say you want the area under a curve, the region between the curve and the x-axis obviously, and there's no obvious formula for an irregular shape like that, so you fill it with rectangles. Let's say 4 of them to start, and each has a width and a height that you can read off the curve. So you add them up and you get an answer. It may be rough, but it's still an answer. The rectangle corners poke above or below the actual curve, and you don't want this, so you use 8 strips instead. The rough edges shrink, and then you move to 16, and you move to 32, and each time the shape gets closer. Now let's say we infinitely increase the amount of strips. Each one is infinitely thin, and the error slowly disappears. What remains is the exact area. Now here's the part that surprised me when I first understood it properly. These two ideas look nothing alike. One is about a single point, and the other is about an entire region, and yet they both undo each other. If you integrate a derivative, you get back where you started. Differentiate an integral, you get the same. They're inverses. The way multiplication and division are inverses. This is the fundamental theorem of calculus, and is why calculus is one subject and not two unrelated ones. The connection isn't a coincidence. It falls out of what the two operations are actually doing geometrically. Once you see what calculus is actually doing, you start to see it everywhere. Velocity is the derivative of position. How fast a position is changing right now at this exact second. Acceleration is the derivative of velocity. Both are just slopes, the curve under your position over time, zoomed in. In medicine, the total drug absorbed by a body is an integral. You take the concentration curve and you find the area underneath it. That area is the dose your body actually received. And we also see it in economics and neural networks and AI as well. It really adds up. Zoom in until it looks straight. Slice until the error disappears. That is generally all calculus ever does. The formulas are shortcuts, good ones, worth knowing, but they're answers to questions that calculus already knows how to ask. Once you understand the questions, the shortcuts explain themselves. Newton and Leibniz invented this in the same decade, completely independently, on opposite sides of the channel. Same mathematics, different notation. The fact that two people arrived at identical ideas by thinking about the same physical problems is worth sitting with. Leibniz notation, dx, dy, the integral sign, survived for a reason. It mirrors the geometry. His symbol for the derivative looks like a fraction because, at its core, it is 1. Rise over run, with the run going to 0. Every formula you memorize is just this idea applied once to a specific curve. The rule for differentiating x squared isn't magic. It's what you get when you run the limit definition and simplify. Next time, the number E, Euler's number. It shows up in finance, biology, physics, and nobody put it there. It just keeps appearing. That's what we're looking at next.